So this video lecture is about the convolution theorem, a very important result. And before we start, let's give the definition of the convolution. Let's say that f and g are two time domain signals, two time domain functions. Their convolution is a new function denoted by f asterisk g. By the way, this is exactly why you shouldn't use the asterisk to denote multiplication of anything. The asterisk is reserved to denote the convolution, otherwise there might be confusion. So the convolution is a function f asterisk g, which is defined by this integral. It is another time domain function, so it is a function of t. It is defined by the integral of the first function times the second function evaluated at t minus tau. The integration is with respect to tau, and it is from 0 to t. So this is, of course, this is a new formula for you. So let's do a few examples to familiarize with it. Take two time domain functions, take t and t squared, and let's try to determine the convolution of these two. So f asterisk g, the convolution of these two functions, it is the integral of the first function times the second evaluated at t minus tau. So it is tau times t minus tau squared, integration with respect to tau, and this is an easy integral to determine. There is nothing complicated here. Let's do one more example. Take f be sine of t and take g be t squared. Then the convolution of f with g is a function f asterisk g of t, which is the integral of sine of tau times t minus tau squared. And you can write sine as minus cosine derivative. And it is clear now you can apply integration by parts, and the rest is quite easy for you to figure out. And we have that t squared plus 2 cosine t minus 2 is the convolution of sine of t with t squared. Most importantly, however, is to have a more visual and geometric understanding of what the convolution does. So take this sinusoidal function, it is sine of t, and the exponential, and let's see what the convolution of these two looks like. And what it looks like is that it looks like both. It looks like the child of these two functions. It looks like a sinusoidal, it goes up and down indeed, it looks like a periodic signal, but it also kind of converges exponentially to something. Or take a sinusoidal function, take a sine, and take another sine of a different frequency. So it is like we are mixing the two functions, right? So the result has both frequency components, both slow one and the fast one. Or take a sine of t and t squared times exponential of minus t, a function that has a graph that goes up and then converges to 0. And indeed the convolution looks really like the child of these two functions, because indeed it goes up, you see that little peak in the beginning, and then it converges, it goes down to sine, something that looks like sine of t. So the convolution, as we can see in this very nice figure I found online, creates children of functions, so to speak. You see here SpongeBob and Teenage Mutant Ninja Turtle, and then the combination of these two has characteristics of both. The convolution has some very nice mathematical properties, so it is symmetric. F asterisk g is equal to g asterisk f. It has the property f asterisk g plus h is equal to f convolution g plus f convolution h. It is associative, so f asterisk g asterisk h is equal to f asterisk g asterisk h. and the convolution with 0 is 0. So it has quite a few nice and convenient properties. Now here comes where convolution meets the Laplace transform. Take f and g, be two time domain functions which have Laplace transforms f and g uppercase. Then the Laplace of the convolution is the product of the Laplace transforms. We can say that the Laplace transform maps the convolution to multiplication. Therefore, if you take the inverse Laplace transform on both sides, the inverse Laplace transform maps multiplication to convolution. Inverse Laplace transform of f times g is f convolution with g. And you can find the proof in the textbook. Let's give an example to see how it works and why it's useful. So let's find the inverse Laplace transform of this function. I'm confident you can do it. It has a double pair of imaginary poles, but let's examine a different way to approach this problem. First of all, we can observe that this function f can be written as a product of two functions. So that square in the denominator we can simply write as s squared plus omega squared times itself. Okay, so we have split f uppercase into two parts. And in the first part, we have multiplied and divided by omega for obvious reasons, which are that omega over s squared plus omega squared is the Laplace transform of sine of omega times t. Now, by the convolution theorem, here we have a product, right? So if you apply the convolution theorem, you have the inverse Laplace of a product of two functions, which is equal to the convolution of the inverse Laplace transforms. And what is the first one? It is 1 over omega times sine of omega t. And what's the second one? It is cosine of omega t. And this is the result. So the inverse Laplace transform of this given function is given by convolution. Do you have to determine the convolution? It's up to you. But it's also fine if you keep it like that. The result is simply given as a convolution. Now, if you really want to do it, you can do it as an exercise, and you can find that the inverse Laplace transform is indeed equal to t over 2 times omega times sine of omega t. Here's another example. So we can use the convolution theorem to find that s over s squared plus 1 cube is given by that function. Now, clearly, this will be a convolution of 3 functions because we have s squared plus 1 cube. So this is s squared plus 1 times s squared plus 1 times itself once again. And you can apply the convolution theorem, which gives you that L minus 1 of f plus g, f times g times h is the inverse Laplace transform of f, convolution inverse Laplace transform of g, convolution with inverse Laplace of h. And with that, thank you very much for watching.